Okay, so my name is Máté Kovács. Welcome to the Tokyo Rust meetup again. Thank you for coming. A few facts about me. I love simulation. I love C++. I used to be a huge C++ fanboy before I became into contact with other languages. And I've loved Rust as well. So today's topic is very, very special to me. It has a special place in my heart. Okay, but seriously. I have a lot of slides, almost 90 slides, and 40 minutes. So let's get this party started. Here are the key takeaways. If you fall asleep after this slide, you're still golden, as long as you remember what's on this slide. So before you jump to rewriting something in Rust, especially if it's like a giant C++ library, consider that maybe you're better off just putting a thin Rust wrapper around it. And this actually might be easier than you think, thanks to excellent tools that were developed by the Rust community. And also, don't panic. Remember that the heap problem can be solved in 6 simple steps. The overview is I'm going to talk about rewrite versus wrap very briefly. And then our lab rat tonight is going to be MFEM. More on that later. I'm specifically going to discuss MFEM from a user's perspective. And then I'm going to talk about the MFEM wrapper that I wrote in Rust in detail, talking about its top-level structure, the low-level Rust FFI bindings that use CXX, the idiomatic Rust layer, and a little bit about future work that I plan to do. All right, so first about rewrite versus wrap. When you're thinking about rewriting something in Rust, you need to think about these 4 questions first. So the first one is, do you understand the internals from the point of view of an expert? Because if you don't, you're likely not set out to rewrite anything. The second one is, do the internals have bugs? This, again, you need an expert's understanding to kind of decide whether there are bugs or not. For example, memory safety issues. And third, even if there are bugs and you know about them, are you sure that rewriting is the thing that will fix all those problems? Maybe there are other approaches. You can always just consider contributing to the original thing. And last but not least, are you willing to put in potentially a huge amount of effort in making this thing that's going to be new and it's going to have its own flaws? All right, so compare this to when to wrap things, you just need to think about, like, did I answer no to any questions on the previous slide? Then you're going to be in here wrapping stuff. And the only thing you need is, do you understand the API from a user's point of view? As long as you do have that understanding, which is much easier to get than an expert's understanding of the internals, you're in good shape for putting a wrapper around it. Okay, tonight's lab rat, MFEM. What is MFEM? It's a free, lightweight, scalable C++ library for finite element methods. I'm not sure about what lightweight means in this context because it's absolutely monstrous. At the very end, I can pull up some like architecture diagrams that were automatically generated if you're interested. It's developed by the Lawrence Livermore National Laboratory in the US. It has too many features to even list here. If you want to learn more about it, you can just go to mfem.org. It has a lot of fancy graphics and visualizations in its gallery. And oh, by the way, the correct pronunciation is MFEM. Please don't replicate my bad pronunciation of MFEM, which is going to be, unfortunately, consistent throughout this talk.
What does it stand for?
I believe M stands for modular, and FEM is just a finite element method. Okay, so this is what my golden week of code looked like. My goal was to try to wrap MFEM in Rust. I was targeting a concrete use case. MFEM comes with a bunch of examples, so I picked out example 1, and I minimized it. I wanted to rely on automation as much as possible, and I still use handwritten glue in a couple of places, but I really wanted to minimize that. More specifically, I wanted to encode ownership rules into the Rust API. MFEM has a lot of implicit ownership rules that you can only learn about by reading the source code, and it makes it, these things make it very error prone to use. Sometimes you just get seg faults, you don't know why, you crawl through the code and you find like, okay, it's because of that. So wouldn't it be nice if the Rust compiler would just tell you, hey man, you're not using this correctly? And I wanted to provide a layer of wrappers on top of all this to support writing idiomatic Rust code and still use MFEM. What MFEM looks like from a user's point of view is as follows. You need to know very briefly about two things. You need to know what the finite element method or methods are, just very basics. And you need to have some basic understanding of key entities and relationships in MFEM. So I'm going to talk about these. First, about the finite element method. Really, the bare bone basics is your goal is to create some sort of computational model of physics, physical phenomena. And generally, in the physics side, you deal with continuous functions that are defined on the continuum of space. But you want to turn these into finite sets of variables that you can actually work with. And if you're familiar with the math, then you really just want to move from the world of functional analysis to algebra. I think algebra is way better known than function analysis. So here's a diagram. Let's say you're solving the heat problem. More on this a little bit later. You have this heat sink, and you want to know, oh, if I heat this thing, what's the temperature going to be? I can ask the temperature at any point on the surface or inside the body. I should be able to answer that without actually performing the experiment, just using a computer. So that's kind of the trick, right? So this is what I want. If I start heating this thing here, then some temperature function is going to form, and this is what we're solving for. So in more precise terms, we're looking for a function that tells us the temperature at a point in space, really any point in space that's inside the body. This function is defined. And we're looking for what's called a steady state solution, which means in the infinity, if you just let the system sit for an infinite amount of time so that all the transients settle, the temperature equalizes, then you're going to get this heat distribution. Sorry about that. I was going to expand what this equation means in terms of the actual partial derivatives. This is the Laplace operator, if you're familiar with. It just sums the second order derivatives. And you usually also have boundary conditions when you're trying to solve a problem like this. In here, we're just going to say that the temperature is 0 on the surface. The goal, again, is to find u, the temperature function. As a margin note, just really quickly, kind of an important issue here that it's an important gap that MFEM finite element methods bridge is that all the physics is analog, but all the computers are digital. So we need to do something that allows us to use computers on these analog problems. And if you're familiar with math stuff, there's a kind of like deeper truth here. It comes from the fact that the cardinality of the set of real numbers is larger than the cardinality of natural numbers. And any quantity, bit pattern, whatever you have that you can hope to represent in a computer is just going to be a natural number. Maybe it's going to be a really big natural number, but it's never going to be a real number. You can't represent real numbers, all of them, in a computer. Anyway, so again, we have our continuous domain. And this is one of the key ideas of finite element methods. We're going to break it up into smaller parts. This is called discretization. And when we've done this, what we have is a mesh for this domain. And then we're going to look for a discretized function on this domain, which we'll call a grid function. Yep.
Is this like just on the surface, or is this actually like a voxel?
Good question. It's not just on the surface, it's everywhere. Yeah, so they are voxels if you're dealing with 3D things. Good question. So then once we have this, some oracle gives us this grid function solution, then we can reconstruct the continuous solution based on that. It's going to be an approximation, but it has meaning in real continuous terms. Okay, so this is the perfect segue to the key entities. These continuous abstract functions in MFEM are called coefficient. The discretized ones are called grid function. Mesh, again, is a discretization of space. We need this to define grid functions. And then finite element collection is a collection of a finite set of interpolating functions. We also need these things to define grid functions. And then we'll have linear forms and bilinear forms. These are things that operate on grid functions. So if you have one grid function and the function takes that as the argument and it returns a number, that's a linear form. It's called linear form because these things are going to be linear by their definition. And if it's a bilinear form, then it takes two grid functions and returns a number. All right. Quick demo, just so you know I'm not bullshitting you. OK, so I'm just running through Cargo this example one that I have transcribed in MFEM sys. And it's going to take a mesh as an argument. I'm going to do something real quick. I'll show you what the mesh looks like. I can just delete that. All right. There you go. So this is a mesh. And you can't see it here, but it's not just a surface. This is like a voxelized kind of representation. Let me see if I can cut it. OK, if I cut it, it's not showing me the, oh, there you go. So now you can see the cells. I can like kind of change the angle of this clipping plane so you can see the little elements in there, right? So what we're looking for here is we want to get a solution to the heat equation through using this mesh and getting a grid function back. And if I, so it's actually, this thing has, I've already ran it, and it output another file that I can feed into the same visualizer, which is, it's .gf for grid function. So now I've loaded it up. Zooming in a little bit, and you're like, OK, this is boring. But remember, we said that temperature is 0 on the surface. So again, I have to cut it, and then you're going to see the interesting stuff, which is on the inside, this function is varying, and it's a smooth function, even though it's represented in terms of discrete sets of values. OK, and this, by the way, it's not specific to, it's not tied to this particular mesh, so I can just take another mesh and rerun the same thing, and it will do its thing. All right. I should probably speed up a little bit. So this is the heat problem. I'm just putting these on so somebody who understands the physics can see that I'm not talking about just hot air. We're really, what is going to be interest to us here is these two forms. The bilinear form is on the left here, and the linear form is on the right. And again, what we're trying to do is we're trying to find U such that for all V, this relationship holds between the bilinear form and the linear form. And I have no idea, by the way, how any of this works. I just went in and read the MFEM documentation. OK, so this is the outline of example one. Just remember, if you're trying to solve the heat problem with a finite element solver, this is what you need to do. You need to load a mesh. You need to create a finite element space. You need to create a grid function and initialize it to something that satisfies the boundary conditions. Then you need to create your linear and bilinear form, translate these things to a set of algebraic equations, solve those equations, and then translate the solution back to a grid function and save it to a file. So this is what we're going to do. This part is about the wrapper. There are no more integrals in the talk, I promise. Top-level structure. It's a monorepo with 3 layers. Each layer is a separate cargo package. MFEM CPP just provides the CPP MFEM library as a cargo package. So it's using some build.rs machinery with the CMake crate to build stuff, or hook into the MFEM that you already have installed in your system. MFEM sys. This is the sort of community naming convention for low-level binding crates. They're always called something sys. It uses CXX to create safe bindings. to the C++ code, encoding ownership rules and whatnot. And then MFEM is going to be the crate of the high-level wrapper stuff that supports writing idiomatic Rust code. All right, very briefly about MFEM CPP. It provides a specific version of MFEM. That version is in fact encoded into the version of this crate itself. It has a feature called bundled. It is on by default. When it's on, then MFEM is built from the sources that are bundled internally. And then if you have it off, then it's just going to use CMake to attempt to find MFEM installed on your system. And it just provides some rudimentary machinery for MFEM sys to hook into so it can find MFEM, regardless of whether it was built from source or you have it installed in your system, link against it. This setup, the whole setup, by the way, was copy-pasted from Brian's excellent Open Cascade RS crate. Thanks, Brian. And it worked flawlessly. All right, the details. Like I said, it's just a simple build.rs file to run CMake. I'm not going to talk about any of the more details here. Please read the code if you're curious. All right, on to MFEM sys. It depends on MFEM CPP, like I was saying. It provides a safe FFI, which stands for Foreign Function Interface, to use MFEM. Uses the CXX crate, encodes ownership rules into Rust type system. This is the most exciting part for me. And also, as a bonus, turns various MFEM int constants into type-safe Rust enums. All right, so what is CXX? It's a safe mechanism for calling C++ code from Rust. As it says, it's in manual. It guides the programmer to express their language boundary, where Rust and C++ are semantically very similar. And then it fills in all the low-level details, so you get a safe binding automatically. In a diagram, it looks like this. You basically you write a Rust module, you put this annotation on top of it, and then CXX will take it, generate some Rust code behind the scenes, and also some C++ code that have hidden C ABI connecting them. So this means the resulting FFI bridge has basically zero overhead, no serialization, no copying, no runtime checks, no allocation. What this looks like concretely in your code is you have this FFI module, you annotate it with a CSX bridge attribute, and then you can put your shared Rust types here that you want to share between the C++ and the Rust bits, and you have an unsafe extern C++ section inside of which you use a Rust-like DSL to describe the function signatures that you want to hook into. And you can also expose Rust things to C++. I have not explored that at all, so I'm not going to talk about it. But back to this unsafe extern C++ thing, then you can actually mess up here. If you mess up a function signature, then CXX will still eat that and generate code. But the catch is it generates C++ code that has static asserts in it. So if you, for example, claim that some function takes an integer, but it actually takes a float, the CXX will eat that, but then the compile time assertion will fail. So you get a compile error saying something is not working out here. Because of that, it's statically safe. All right, so we're translating example 1 into the MFEM sys provided machinery. Just remember these 6 steps. We're loading and refining a mesh. In the original code, it looks like this. I have not touched this code at all. This is coming straight from the MFEM example. Nothing exciting is going on here. We're just loading the mesh, and then we're deciding on how many levels we're going to refine it to, and we just run a for loop. All right. And then on the Rust side, this is Rust code using MFEM sys. We have to deal with a bunch of these annoying details of we need to create a string that we can pass to C++. The CSX crate gives us helpers for doing this. So we can call this constructor-like function that I'm going to show you in a little bit. And then we're just doing pretty much the same thing. So the catch here is that everything that constructs a thing in C++ and returns that to Rust has to return a unique pointer. So it requires some handwritten C++ glue code. And the sort of deeper reason for this is that C++ and Rust disagree on what a move means. In C++, a constructor is always involved in moving things. In Rust, that is not true at all. And in Rust, you don't really have constructors. In C++, a constructor doesn't return anything. It more like uses a piece of memory to in place construct something. So anyway, long story short, we need some handwritten glue code that looks like this. This is C++ code. And we're going to hook into that by actually using it twice. We're going to use the same function because it's templated. And I also learned this pattern from Brian's Open Cascade RS crate. So moving on, once we have this in place, it's easy to translate the methods. Everything is pretty straightforward, especially if you remember a pin from Alan's talk last time. When you need to mutate something, it can't just be a plain mutable reference. You need to pin it so it doesn't move in memory. Apart from that, we also have some methods that I call dirty because they require a handwritten C++ glue. That's because get nodes needs to return a result. On the C++ side, it returns a pointer that may or may not be null. We don't want any of that business in Rust, so we need to provide a wrapper. And then the other thing is all these FFI exposed types from the C++ side are opaque. So if they have fields that you would normally access in C++, like this example is doing here, actually it's not doing it right, never mind, some other slide, then you need to provide these accessor functions so you can actually get to them. This is what it looks like, and this is a pattern that I recommend using that Shores taught me, where instead of having the return type on the left in C++, you're going to have it on the right, like you would have in Rust. I discovered early on when I was writing these piece of glue code that it was really sort of cognitively exhausting to see the return types on the left in the C++ code and then look at Rust code that has the return type on the right. So this is kind of a refreshing change. I highly recommend it. And also a sort of nice consequence of this is you can define FN now to mean auto, and then you can rewrite this and it will look like Rust. Actually, please don't do that. It's bad. All right.
That way your variables can be FNs too.
Exactly. Who knows what that
Your
means?
lambdas can be FNs.
I'm going to stop you there. All right, so I was talking about this get nodes stuff. This is what the C++ glue looks like. And I put the Rust function signature on top for you to see. So you might be wondering how this works, because we have a result on the Rust side, but the C++ function is just returning a bare reference. And by the way, we check the pointer internally, and if that pointer happens to be a null pointer, then we throw an exception. So surely there's some mechanism that turns that exception into the error branch of this result. And that's exactly what's going on. This is provided by CXX again. This is the pattern. If you want to use this pattern, and you probably should, then you can just read about it in the manual. There's nothing tricky going on. I'm just defining my own MFEM exception type. And that's what is being thrown here. All right, moving on. Now we are ready to create a finite element space. There's a lot of dirty stuff here on the C++ example. A pointer is involved, which may or may not be null, so we need to remember whether we need to delete it or not. And anyway, but at some point we get to this part where we have the finite element collection and the mesh, so we can create the finite element space. Cool. So in Rust, this is going to be, again, much more annoying. We don't want bare pointers, so we're going to emulate nullable pointers, an option of a unique pointer. So when this guy is none, then that means we had a null pointer on the other side. And as you can see, this is very verbose. We have to deal with the low-level details of upcasting values and whatnot. So here we're actually upcasting this H1 FE collection, which is an subclass of finite element collection on the C++ side to just be an FE collection pointer. And anyway, this is not super interesting, but we're constructing the finite element space finally, and this is where we're going to get into, not this first, but the implicit ownership stuff. So if you look in the MFEM documentation for this finite element space stuff, you'll notice that internally it's holding pointers to the mesh and the finite element collection. But then the documentation says these things are not owned. So this is an example of an ownership rule that is not explicit. You have to know this, and the only way to know this is to actually read the code, because if you just look at the constructor, you have no idea. You're passing in pointers here, and anything might happen. Maybe it's going to hold on to those pointers, and it's going to become responsible for freeing them or not. You just don't know. But in Rust, we can encode all these things, and the way to do that is by putting lifetime annotations on this type. Again, this is in the unsafe extern C++ part of the FFI module that CXX is going to parse. So CXX understands these lifetime annotations, and this will allow us to, for example, in the constructor where we need to pass in references to the mesh and the finite element collection, we are able to propagate the lifetimes of the mesh and the finite element collection to the type, to the finite element space that we're returning. So now the Rust borrow checker is sort of in on the joke. It understands this thing is holding references to other things. So, for example, I had it's definitely my favorite feature of CXX. It helped me find a bug that was causing a segmentation fault, where the finite element collection was just in a unique pointer that was going out of scope, getting dropped. And after that, I was trying to use the finite element space that was holding a reference to the now freed nothing. So I think it's a good sort of example of how smart pointers definitely help. Well, I mean, we're using unique PTR all over the place, but just keep in mind that borrow checking is even more robust than that. And one easy reason to understand like why that is because borrow checking uses information that is no longer available at runtime. So smart pointers are ultimately runtime machinery. They can't have knowledge of things like types and lifetimes and whatnot. And borrow checking does. So it's going to be more precise in describing these things. All right, on to creating and initializing a grid function. Nothing exciting is going on here, except because we can't overload operators in Rust. I mean, we can't overload the assignment operator. That would always mean a move, so it's special. We need to create these annoying wrappers that look ugly when we use them. All right, we're halfway through. How am I doing on time? What's left to do is we need to create the linear and bilinear forms, solve the set of algebraic equations, and bring the solution back to be a grid function, save it. All right, just a quick reminder, we're dealing with a heat problem. So we're interested in this particular bilinear form that takes the dot product of the gradients of these two things. And then we have this linear form that's essentially just a dot product. So if you were to go in and dig through the documentation of MFEM, you would find, diffusion integrator, it claims to be exactly this bilinear form if we set Q to a coefficient that is constant 1 everywhere. So diffusion integrator is going to be our bilinear form, and then this other thing called domain LF integrator, it stands for domain linear function integrator, is going to be the linear form. We're setting this up. This is the linear form setup. Again, things are more verbose here on the Rust side, mainly because we need to deal with explicitly upcasting things to base class references pointers. And then same with the bilinear form. Now we're good to translate everything to algebra. This is what it looks like. It's not super exciting. You can see on the Rust side, it's easy to see what is being mutated. So everything that's being mutated is passed in by pint mute. And again, some annoying upcasts are happening here. So we need to cast a grid function to be a vector, and also a linear form to be a vector. By the way, all of these things that contain arrays of numbers, as far as MFEM is concerned, at some point as you go up and up in the hierarchy, they just become vectors. Yes?
Are those pins heap pinned or stack pinned?
I don't actually know the difference between a heap pin and a stack pin. Sorry, so I
Okay.
don't know how to answer that question. Yeah, I'll find you after the talk. Where was I? I was here. Okay, so we're solving the equations. Again, the code is much more annoying on the Rust side because we're dealing with explicit upcasts. And we actually check that things that are not supposed to contain null pointers are not null pointers. Cool, and then this is pretty straightforward again. We're just translating the solution back to be a grid function. We're saving that, and it looks reasonably similar already. Again, on the Rust side, we need to deal with the annoyance of passing in the mesh file name and the solution file name as C++ strings, which the CXX crate is helping us do. All right, we're done with example 1. Here are the key points for building these low-level Rust FFI bindings with CXX. You want to use the construct unique pattern and the try catch to result pattern to handle exceptions. Try to make the C++ APIs implicit ownership rules if there are any explicit in Rust. And don't be afraid to get your hands dirty and write a bunch of C++ glue code if you need to. Sometimes you can't avoid that. For example, I had to write a bunch of these upcast type of functions that are annoying, but they basically write themselves and they have no cost at runtime. They really just erase type information. And try to expose type-safe enums to Rust whenever you can. All right, moving on to MFEM. We're in the final stretch. I think we can finish before the pizza gets here. So this is going to be the idiomatic Rust wrapper. It depends on MFEM sys. It's trying to hide the sharp bits like unique PTR, C++ strings, and whatnot. Also turns constructor like FFI functions into self-new or self-from something something. Exposes real methods. Provides field setters and getters. And this is going to be the most exciting point. Turns C++ base classes into traits. This is kind of important. And then hopefully it has identifiers that follow Rust best practices. And again, just remember, this is the outline of example 1. Load the mesh, create a finite element space, create a grid function, create linear and bilinear forms, translate to algebraic equations, solve, and then bring the solution back and save it. All right, again, so nothing new on C++ code on top, Rust code on the bottom. It's getting reasonably close. So we can actually call this from file thing on mesh. We're just passing in, by the way, you can't see that, but this args.mesh file is coming from an argument that is done with the clap library, if you're familiar, for parsing command line arguments. So this mesh file field is really just a normal Rust string. We're passing that in. No more screwing around with the C++ string stuff. And then we can ask for the dimension like this. Even though this is capitalized on the C++ side, that's not the custom in the Rust community, so it's lowercase. And then we just call uniform refinement a bunch of times. So I call this the wrapper inner pattern, where you basically just introduce a fresh type that has the same name as the FFI type, and it has a private field that holds the unique pointer to the FFI stuff. And this allows you to then provide an impl that has all the machinery that you want, like a new, from file, and so on and so forth. Now I can create the finite element space. Again, this is painful because we still have to deal with the option stuff. We just can't use pointers that might be null. We don't want to. So this is more exciting. This is the base trait pattern. In C++, finite element collection, like I was saying, is a base class. A bunch of things inherit from it. But in Rust, there's no inheritance. So we have to do something about this, and we make it a trait instead. And if you think about it, inside of machinery that this trait will contain, we have to get a dynamic reference to something that is a finite element collection in Rust. And we have to upcast it so that on the C++ side, when we're calling into the FFI machinery, we actually have either a reference or a pointer to the FFI finite element collection. So we introduced this S-based trait. And here's an example of how to use this. So in C++, H1 FE collection is a subclass of finite element collection. In Rust, we're going to make it implement the finite element collection trait. The trait here actually is empty. It only has default implementation, so you can't see anything. But it forces us to implement S-base finite element collection for H1 FE collection. And the way we do that is we grab the inner reference that is a shared pointer to H1 FE collection on the FFI side. And we pass that into one of these hand-rolled pieces of glue code of a function that is doing the upcast to a finite element collection. All right, so we can create and initialize the grid function now. Almost the same as before, except now it's set all as a real method. And again, we're almost halfway. We're halfway done. We're almost done. What's left is linear form, bilinear form, algebraic equations, solving those, and then bringing things back to a grid function. This is getting pretty close. On both sides, it's almost the same. If you notice that I could have inlined constructing the domain LF integrator in here, and then it would be the exact same number of lines. I'm just doing this for readability. And notice that there are no more explicit upcasts, even though we are creating a constant coefficient here. And this domain LF integrator wants just a coefficient. It signals that by having that trait in its signature. There's no upcast because we have the S-based stuff. All right, and then the linear form, very similar. Translation to algebra. Again, the only difference here is now form linear system is an actual method on the bilinear form. And again, if you compare the C++ side on the left with the Rust side on the right, it's easy to tell what are the things that are the outputs here. In C++, it's a little more difficult to see, but it's going to be capital X, capital A, and capital B. We're solving the equation. I'm not going to talk about this in detail. The only thing is PCG, the function name is capitalized. In C++, we're just going to replace that with something that's more descriptive, solve with PCG. PCG stands for preconditioned conjugate gradient, by the way. And translating back and saving the solution looks like this. I'm pretty happy with it, how it turned out. And yeah, we're done with this too. So I can just show you that we can run this as well. So instead of running things in MFEM sys, we're just going to run example one from, and it has a bunch of these ugly warnings that needs fixing. Sorry about that. It's doing the same thing. All right, so key points of building these idiomatic Rust wrappers is try to hide as much as the FFI specific machinery as you possibly can. These things are kind of ugly. The user doesn't need to know about them. Use the wrapper inner pattern to give easy access to constructor-like functions like new, from thing, methods, getters, and setters. Use the base trait pattern to encode inheritance. I think this is probably the most important takeaway. And then choose identifiers that adhere to Rust community standards just to be a good citizen. All right, so this might look like a lot, but actually MFEM is huge, and I barely scratched the surface. It's basically almost no coverage as far as the examples are concerned. So one main thing to do here is just incrementally extend coverage and slowly translate all the examples one by one to idiomatic Rust code. And as part of this, contribute improvements back to upstream MFEM. Like I often found places where it is quite obvious that some method on the MFEM side should be const. They just forgot to make it const. But it's easy to see from, like, once you transcribe these things into Rust, that if that thing is not const, you can't do a lot of the things that examples are doing. So it must be true that that thing is const. MFEM is an old library. People have been using it for a long time. So I think it's reasonable to assume that it's actually doing what it claims to do. It's just the API is not perfect. So it's easy to contribute these improvements back by going over to the MFEM repository on GitHub and filing an issue saying like, hey, should this method be const or something like that. And it will actually improve MFEM, the C++ library itself. So it's kind of nice. And then once that is done, it's actually possible to simplify some of the C++ glue code in MFEM sys. All right. And then another big thing is MFEM, all the machinery in it uses MPI, which stands for Message Passing Interface, which is a big thing in the high-performance computing world. It's basically allowing MFEM programs to use very efficiently large clusters of computers to parallelize execution. And this is a really big thing. It can cut down the execution time of workloads to like 100th. So it should really work, except it's kind of difficult. It's probably the most difficult item on this list, because when you're compiling something with MPI, you're basically compiling with an MPI-aware C++ or C compiler. So it's putting a bunch of instrumentation in the code they can't see. It's really complex, very, very error-prone. But there's a sort of sliver of hope here, just that there's an MPI crate on crates.io that seems to be actively maintained, and it has examples and a bunch of things. So I'm hoping that eventually this MFEM wrapper will be able to work with that. And then the last thing is, like I said, MFEM is a monstrous piece of a C++ library. It has a lot of components that are disabled by default. But if you're trying to do any serious work with MFEM, you kind of need to enable some of them. Probably the best example is Hyper. It's a very efficient linear solver library that is also maintained by the Lawrence Livermore National Laboratory. So it's like a sister project of MFEM. And MFEM is very heavily using Hyper in its parallel, like MPI mode, if you have that enabled. So that should probably be first on the list. And that's all I got. Thank you for listening. The code is open source. You can check it out on my GitHub. It's MFEM-RS. Don't get confused. I also have the normal MFEM C++ library forked as just MFEM. And if you're interested in this sort of stuff, like you like Rust, you like C++, simulation, low-level things, but you also like learning about new things, finite element methods, consider applying the Braid, where Shors and I work. That's our website. And I wanted to say special thanks to Brian Schwind, who taught me a lot about the CXX crate, and whose Open Cascade RS, as you can probably tell by now, serve as both as an inspiration and a copyable project setup, which cut down development time. Thanks, Brian. Also, Shors, who taught me a lot about the ins and outs of modern C++, how to write good modern C++ code, which is actually possible. You just have to learn it and be disciplined about it. And last but not least, Guido and Ivo, founders of Braid, who continue to answer my questions about finite element methods. I tend to be really bothersome when I don't understand something. All right, that's it. Do you have any questions? I'd be happy to answer them.
I'd like to ask, how about the proportion of your glue codes, the proportion, the percent of your glue codes according to all of the code you write?
What proportion? Sorry, what proportion?
C++ glue code. So you write many C++ glue code?
Yes.
Yeah, and how about the proportion or percentage?
That's a good question. I don't actually know.
Yeah, because I saw there might be so many glue codes. Like if you want to convert one C++ class to its base class, you have to write one glue code. So generally speaking, if I want to write one library to Rust, maybe I have to write many glue codes. So
I'm afraid that's probably true. So according to GitHub, about 86% is Rust and 14% is C++. I think that's not bad, but I agree. I did have to write a lot of these C++ shims. I think if I knew more about C++, I could probably use some machinery like macro or something to auto-generate a lot of these. I just didn't want to spend time on that.
yeah, because I think it might be, maybe can be solved with like something like the template or, yeah, but I'm not an expert about it. And my second question is, yeah, I see you want, in your future work, you want to extend your library with MPI. And yeah, because I just want to export my linear system software, which is OpenPM to Rust, because OpenPM is quite similar to MPI, which relies on GCC. So if my question is, if there is no any implementation of OpenPM in Rust, so where should I start, or can I move down this? Yeah.
That's a good question. I don't actually know much about OpenMPI. I've only used it in C++. So I don't know what the state is. OpenMP, sorry.
Because I think the workflow of exporting it to Rust is quite similar, like exporting MPI to Rust. But if there is no implementation right now, so I don't know whether it is possible to export.
If I may.
I also don't know. I'm sorry. I would look at if I were you, I would look at the MPI crate, because, like you said, they're kind of similar, OpenMP and MPI.
Maybe I can add a little bit to that. So the OpenMP part is actually compiled within MFEM. So it's also a dependency of MFEM. So you have OpenMP and MPI fighting each other.
Yeah, I think the OpenMP code are generated in the compile time. So I think there are specific OpenMP related check during the compile time. Yeah, like if you correctly use critical or share some kind of that check. So if I write my own package, should I add it?
So all I can say here is that we're lucky that none of the OpenMP stuff is actually exposed on the MFEM API. So as long as that is hidden within C++, you're good.
You don't really have to specifically deal with it?
In our case, we did not have to explicitly deal with OpenMP. Next question.
I'm particularly interested in the base class translation to trait. So for things that are just functions, it seems like it might be pretty straightforward because you're just trying to get new functions that are wrapping and all that. But the thing with inheritance is that you can have actual fields described in the base class, whereas in traits you can kind of do that, but that would effectively be giving access to the internals using references of some sort, right? Either mutable references or immutable references. but a very common issue that you have in Rust is that, which a lot of new people have, is they try and reference one field immutably and another field mutably, only to find out that the way they got that reference was through a function, which means that you have a collision because you didn't extract all the references at the same time, and they can't do that without pattern matching, right? So you have to create a function that pattern matches internally and then gives you the immutable reference and immutable reference, or all the immutable references, whatever it is. So how does that work out?
That's a good question. I don't actually know. I can show you a little bit more about the code because there are some details here that I kind of glossed over. All right, so let's go in here. So I actually have not one trait, not just as-base, but I also have as-base mute for getting the mutable thing, and then I also have an into base, which helps you upcast something like a shared pointer when something needs to take ownership of the thing as the base class pointer. And I don't know if any of this is helping. I'm just showing that it's a little more involved than I explained. And actually, I think that there are probably things that you can't do through this pattern that you can do in C++. But I think a lot of those things turn out to be things that you should not be doing anyway. Like, like holding both a mutable and an immutable reference to something.
Thank you. There you go.
For the result API, sort of converting from C++ to Rust results, are exceptions the only way to sort of return results from the C++ side?
As far as I can tell, yes.
Okay. I'm not much of a C++ user. I know some game devs will turn off exceptions for performance reasons. I wasn't sure if there's some other way to tell CXXRS to return results. Exceptions are
I guess, okay, so I'm actually, this is not, what I'm saying is not entirely true.
Maybe I should read the website now.
Because, yeah, so one thing that I was deliberately avoiding is, let me try to go back to the, where is my syscrate? Here we go. So one thing you can do here is you can actually take and return pointers if you want. And then you can do this conversion of like checking the pointer, for example, one layer higher in the idiomatic crate to see if you want to return a result. So you could do that. But I think if you want to return a result on this layer, which is the raw FFI, then you have to use the pattern that CXX wants you to use, which is the exception one. I just realized there's another thing which I also kind of glossed over. So I'm just going to show you that really briefly because I think it's good practice. Where is this? Yeah, there you go. So for example, in C++, often you just have these. So this is an anonymous enum. There's no way to talk about this outside of the basis type class. So when you reference these like basis type invalid or whatever, they're basically just int constants. And you can see that on the constructor of FE collection, this is actually an int. So I could pass in any int I want. And I think that's not a great idea. So in Rust, this is expressed as a real enum that has the same values and the same names. And then I just tell the Rust compiler, hey, I want this to be an int.
Sorry.
Thanks for the talk. I have two questions. The serious one and the non-serious one. The serious one is...
Let's start with the non-serious one.
Non-serious one, east cons, west cons, which one do you?
East cons. For East cons, always.
Definitely east because we're in Japan, you know.
I don't know where the contraction was. I think we all set, but you can learn from each other. And the most first question is, with your wrapper, you use some debug locations, I think, and some indirections. Did you actually exclude some probably preliminary performance benchmarks, seeing like how crossing the API boundary actually affects the performance of your program?
I have not done any performance profiling. In fact, I have not touched the code since I got the example working, because I kind of have PTSD from all of this.
Yeah, it would be interesting to see because like these things can probably not entirely be optimized out, especially if you actually do debug locations. I also think like if I don't know the libraries or like there's not many occasions we actually have to cross between C++ and Rust, and it might not be a huge problem. It's just interesting to see. Thank you.
Okay, so I have two quick questions. The first one is, did you manage to use a debugger over both Rust and C++, a single debugger? And second one, what is the most difficult part of all this?
I have not tried using a debugger. I was trying to rely on just the type system to figure out why things were segfaulting on me as much as possible. Sorry, what was your second question?
What was the most difficult part of all of this?
Sort of just being disciplined and muscling through. I have a tendency of getting lost in interesting details. So when I see like a problem, I try to really think about solving, like addressing the deeper underlying issue. But if you're trying to do that here, at least I'm pretty sure if I had tried to done everything here correctly, I would have never gotten to the end of being able to run example 1 in Rust. So I really had to forcefully stopping myself and just thinking like, okay, actually I'm just gonna write the dump wrapper, or I have a bunch of dirty things in here that I can show that should probably not be in there, but they work. A good example is this. I have this sort of thing all over the place because, like I was saying, often the MFEM API appears to not be const correct. So even though something is never actually going to be modified after you pass that in as a reference to something else, it's not taken as a const reference. It's taken as a mutable reference. So if you want to expose, and the problem is that if you expose that on the Rust API, then because you have borrow checking, and the borrow checker is like, no, you can't have a mutable reference to this thing because you're already borrowing it immutably in this other place. So the only way to make it work is to make this reference immutable. And that actually works. It might be papering over a serious issue. So actually, my main question is like, how do I do an audit that's automated that would find all these issues? And there's probably some automated tool that can do that. I don't know. So that it's full of this sort of dirty things.
All right. Before we get to the pizzas, maybe I should ask also a couple of questions. Because as you know, like Máté is always the one that fires them. So let's see how he does with them. I noticed in the love triangle between C++, Rust, and what was it? Simulation? Yes. There was no Haskell. Where does Haskell fit in there?
Well, okay, so it's first, touche. It's a good question. I didn't think about that. I should definitely have tried to incorporate Haskell into all of this. In my defense, I'll say that this is not an exhaustive list of all the things that I like. I also like pizza, and it's not on here.
Doesn't it have the love pyramid?
The tetrahedron, yes. And maybe the standard question, how did you get into programming, and what was your first language?
Yes, so I got into programming, and I tell this story all the time, by being a little kid in the late 90s when games like Doom and Wolfenstein 3D and what else, like Duke Nukem were coming out for the first time. I really loved those games. My parents hated them, by the way. And I just thought I want to make this sort of stuff. And I had no idea about programming or simulation or really anything. I just wanted to do that, so I started learning programming. I by chance, I made friends with a fellow nerd very early on, in like 3rd grade, 4th grade, and he basically taught me some simple things that he knew about programming, and then we were just learning together, like writing mostly graphics demos before GPUs were a thing. Like it was all like software-based stuff, and my first language was Pascal, which I think is an excellent language to learn, precisely because it has strong static type checking, and it's really annoying about pointing out all your mistakes. And I think that's what a person needs when they're learning a new skill. They need to be told and shown all their mistakes. So then, yeah.
I mean, Rust is also clearly good at pointing out everybody's mistakes. But what was for you the most difficult part learning Rust?
Definitely borrow checking. And like I said, coming from a C++ background, I always felt like I used to be able to just do this thing, and now it won't compile, and the compiler is telling me like, you're stupid, but I know this is supposed to work, you know? And then once I learned more about the rules, I realized that they actually make sense. And when you're getting caught red-handed, you're actually trying to do something that would not be safe in some scenarios that maybe you're not thinking about, like when there are multiple threads, or who knows. So to answer the question in one sentence, yeah, the borrow checker, fighting the borrow checker.
All right, very common. I think, you spent your Golden Week here developing this for us and the community. What other Golden Week projects from other people here in the room would you like to see and have them be presented at the Rust meetup?
Oh, that's a great question. I would love to see more game dev stuff. Like I said, I got into computing by wanting to make games, so I made a lot of little games. But in fact, I have made no games with Rust so far. So if somebody had a little game project, I would be happy to help out. I don't know.
All right. Thank you for your talk, for your work. And let's get to the pizza.
Thank you, Shorts.